Hello everyone. In this video, we are going to be looking at one of my favorite theorems from introductory analysis, and it's relating to the numbers to the square root of 2. So, it is known, let's just say, that the square root of 2 is not a rational number. And, there's lots of different proofs for this, but the basic one is, assume it is, and then we find that the numerator and denominator of that rational number, supposedly must have a common factor of 2 always. And that rational numbers don't work like that. They can always be written in lowest form. So there is no rational number who acts like the square root of 2. But what you might not know the proof for is that the square root of 2 is in R. Okay? And that's what we're going to look at today. So, theorem. There exists, try better eating that. Still kind of bad, but whatever. There exists an alpha in R such that alpha squared equals 2. And to be honest, this proof works. You pick basically any number, even real number would work. Yeah, I don't know. That's certainly every natural number would work here, but we're going to use the very concrete 2, but it's not too bad. Okay, well, so how do we do this, right? So, we know root 2 is not a rational number, but we need to prove that it is on the real number line somewhere. It's in the set that we've constructed. And we have to remember what the real numbers are, right? So remember R, R is the complete ordered field. Now, I don't want to spell field wrong because I spelled field wrong in a bunch of in 2 of the beginning videos. And it's a little bit embarrassing, so I'm gonna just make sure that I spell field right. So it's I-E-L-D. Okay, well, enough embarrassing myself about that. Complete. We have different formulations of completeness, but what I mean by complete is that every subset of R that is bounded above as a supremum. Okay, and that's kind of our formulation of completion for this, for the sake of this video. Okay, so we're going to use that. We're going to use that to find this number alpha, and this number alpha is like the square root of 2, right? Its square is 2, so we're going to be proving that the square root of 2 is a real number. Okay, so let's get into it. So proof. Let's say consider the set T, which is, okay, well, let's think about this set. The set T, which is, T is in, it's a real number, such that T squared is less than 2. If we imagine a similar set for the rational numbers here, then this set famously doesn't have a least upper bound, right? There's no least upper bound. But this is a set of real numbers, so it has to have a least upper bound. Right, so we're thinking about all the numbers whose square are less than 2. And so hopefully it makes sense to say that the least upper bound of this set probably is the square root of 2. You could also say we're looking for the set of all t such that t squared is greater than 2, and you find the greatest lower bound. Equivalent, but we will do it like this. Okay, so then we say let alpha equal the supremum oh, sorry, we should be clear here for a second, right? T is, T is a subset of the real numbers. T is bounded above. Indeed. Indeed. If t squared is less than 2, then that means that t squared is less than 4, which means t is less than 2. Right? And maybe that comes from the fact that I know that the square root of 4 is 2. That maybe, we don't need real numbers for, right? We need just natural numbers. So maybe we can conclude here that t is less than 4. Sorry, t is less than 2 for all t in t. So it is a subset of the real numbers that is bounded above. Therefore, t has a supremum. So we can say let alpha equal the supremum of t. And our claim is that alpha squared is equal to 2. And with that claim, we're done, right? So that claim maybe has all the work in it, right? So we're going to prove that alpha squared is equal to 2. And we're going to do this in a little bit of a backwards way. We're basically going to prove that it couldn't be any bigger and it couldn't be any smaller. Now you could get into maybe the definition of multiplication in the reals using, maybe it's construction and things like this, right? To get some sort of other kind of semblance out of this equation, maybe a more direct proof, but a more complicated proof, or maybe I don't know about more complicated, but appealing to the definition or maybe the construction more. Anyways, together today we will be looking at 2 cases. So we're going to say that first of all, we're saying that if alpha squared is less than 2, this violates. Violates is kind of a strong word, but this contradicts. This contradicts that alpha is an upper bound for t. And then the second thing is if alpha squared is greater than 2, this contradicts that alpha is a least upper bound for t. And yeah, so with those 2 subclaims, we get our result, right? So, well, let's just jump into it, I guess, right? So, we get proof of 1. Maybe I can color code it a little bit, so I can maybe make that the red one. Although, do I really want to be writing in red? Well, maybe I do. Okay, I'll write in red for now, unless it gets too annoying. Okay, so let's get into it, right? So alpha squared is less than 2. If we can conclude, we want to show that if this were true, then alpha is not an upper bound for t. That's kind of what we're trying to show. So we're going to say, suppose alpha squared less than 2, okay? Then, again, we're going to show that this is not an upper bound for t. That means that there is an element in t that is larger than alpha, if this is the case. Right? Again, our goal is to contradict the fact that alpha is an upper bound for t. Okay, so again, I'm going to repeat myself. We're going to find an element of t that is larger than alpha using this assumption. Okay, so now consider the number alpha prime, which is alpha plus 1 over n. let's just say alpha plus 1 over n, for some yet to be set n in, whatever you want to, it's going to be the natural numbers. It's a bad n. That's kind of how I draw an n. Our goal is to show that alpha squared is, first of all, the first thing is to note that alpha prime is greater than alpha. Maybe I'll just, not 1, but alpha prime is greater than alpha, right? It's strictly bigger. So if alpha prime is in T, then alpha is not an upper bound for T. So now we need to show that alpha prime is in T, which is equivalent to saying that alpha prime squared is less than 2. Okay, so let's consider alpha prime squared, which is equal to alpha plus 1 over n squared. And the point is that we're gonna pick an n here that makes it so that this number is gonna be still less than 2. So what is this? This is alpha squared plus 2 alpha over n plus 1 over n squared. We know that alpha squared, right, is less than 2, right? So maybe we can say that this is less than 2 plus 2 alpha over n plus 1 over n squared. So this gives us a little bit of room, right? Because our end goal here is to say that this is less than 2. We know that alpha squared is less than 2, but how much less, right? Well, we have to fit all this in there, right? That's the point. We got to fit all that in there, in that little gap. And that's fine. We can do that. Depends on how far below, but it's okay. So one thing, we're just trying to show it's less than 2. So to simplify our work here a little bit, what I can do is I can just say that 1 over n squared, well, I mean, it's less than 1 over n, right? Because n some maybe less than equal, but okay, we'll get a strictly less than in a second. But anyways, it is less than 1 over n. So the point of that is that we can combine this into alpha squared plus 2 alpha plus 1 over n. Okay, and so now the point is that we want to fit this into the little gap, right? So what I mean by that is pick n equals n naught such that 2 alpha plus 1 over n is strictly less than 2 minus alpha squared. The little difference. 2 minus alpha squared, that's some positive number, right? Because alpha squared is less than 2. So we want to pick some n. Alpha is fixed, whatever. Pick some n that makes this work. We're allowed to make this choice because this is the same thing as saying pick an n such that this is satisfied, 2 alpha plus 1, right? It's the same thing. And this can be done, maybe n naught, I guess is what I really mean. This can be done because of the Archimedean principle, or the Archimedean property of R. So this can be certainly done. Okay, so we picked that. So maybe now I'll continue, right? And maybe we'll continue as if it's been that this whole time. 2 alpha plus 1 over n naught. And we're going to, this by definition, by how we define n naught, this is alpha squared plus 2 minus alpha squared, which is equal to 2. And there we have it, right? So therefore, maybe I'll switch colors again. Therefore, alpha prime squared is less than 2, and so, well, and so alpha prime is in T. And this is our contradiction. So if alpha prime is in T, then we have that alpha was not an upper bound for T. And so we get our contradiction. So that's half of it. We know for sure that alpha squared cannot be less than 2, right? That's our for sure thing, right? And so now we need to do the other way, because we still have that alpha squared could be strictly greater than 2. So we're going to do that now. So I'm going to say proof of 2. And remember, proof of 2 is this way. Suppose alpha squared is greater than 2. Suppose alpha squared is greater than 2. Greater than 2. And in a similar style to this, we're going to consider alpha prime. And now alpha squared is bigger than 2. And sorry, let me remind you what our goal here is. We're going to show that alpha is not the least upper bound. We can show that there is another upper bound for T, which is smaller. So we're going to consider alpha prime, which is alpha minus 1 over n this time. And so again, in a similar style for this, right? For some yet to be selected n. We want to note that alpha prime is less than alpha if alpha, right? If alpha prime squared is greater than 2, then, alpha prime is an upper bound for T. But again, in a similar way to this, that contradicts that alpha was our least upper bound, because this is smaller, right? Alpha prime is smaller. And if we can show that it's greater than T, 2, then alpha prime is also an upper bound, but a smaller one, so alpha must not have been our sub. Okay, so similar vibe now. We consider, well, I won't say consider again, but alpha prime squared, which is equal to alpha minus 1 over n squared. And, okay, what is this? This is alpha squared minus 2 alpha over n plus 1 over n squared, right? And again, we're trying to show this is greater than 2. That's our goal eventually, right? Greater than 2. So it's fine if I, start making it smaller. So one thing I could do to just simplify my life here a little bit is that, right? You just get rid of this term, and so clearly we're making it smaller. Okay, again, alpha squared is bigger than 2. So this gives us a little bit of room, right, to fit this in before we get lower than 2. This is something bigger than 2. I'm subtracting something, but I don't want to subtract too much because I want to still be above 2. So we do an extremely similar process to what we did up there, right? So how did I write it? I said pick n equals n naught. Oops. Pick n equals n naught such that, how can we write this? Such that 2 alpha over n is less than alpha squared minus 2. Alpha squared minus 2 is positive. And again, we're allowed to do this because it's the same thing as saying 1 over n is less than alpha squared minus 2 over 2 alpha. And that's a real number, so the Archimedean principle Archimedean property of R is letting us pick some n naught. That makes this true. So then we have that, right? We have that negative 2 alpha over n naught is greater than, maybe 2 minus alpha squared. So we can continue, right? And we can replace this, well, I guess maybe I'm at dot 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 there, right? With alpha squared plus 2 minus alpha squared, which is equal to 2. Right? I just replaced that with something smaller, 2 minus alpha squared, and the alpha squareds cancel, we just get 2. Right? And there we have it, right? So we can basically conclude now, therefore, alpha prime squared is greater than 2. Right? So this implies that, alpha prime is an upper bound for t. And we have a contradiction because alpha prime is an upper bound for t, but is a smaller upper bound than alpha. But that can't be true. Alpha was the least upper bound. So finally, at the end of all this, right, we've basically proven our claim, right? Therefore, there's only one option left. And it's that alpha squared equals 2. And there we have it. That is our proof that the square root of 2 is an element of R. We used properties of what R is, right? It's a complete ordered field. Complete meaning this, a complete ordered field that has Q as a subfield, right? Is what the rational numbers is a subfield. And we broke it into 2 cases, essentially. We said, well, I'm telling you that alpha, which is a supremum of that set, couldn't be less than 2, couldn't be greater than 2, so it must be just equal to 2. And we do that by constructing these alpha primes and showing that, well, with those assumptions, we can make these weird numbers that break the rules of being a supremum. And so we conclude that alpha squared must be equal to 2. And this proof, replace 2 with x. Couple places you need to maybe just barely mention something extra, but for the most part, you just kind of replace 2 with x. Maybe a positive x, right? But yeah, definitely a positive x. But yeah, that's that. Okay, everybody. Well, thanks so much for watching, and hope you enjoyed.